Alright, now we're going to talk about writing complex numbers in polar form. Before we do that though, complex numbers can be represented geometrically. So that means if I have a complex number 3 plus 4i, the 3 is my real part. So if I come over here and look at my xy axis, the x-axis is the real axis. The y-axis is technically your imaginary axis. So therefore, if I have 3 plus 4i, technically, as an ordered pair, I can write that as 3, 4. So if I come over here, I go over 3, then up 4 units. So 1, 2, 3, 4. So that would be there about. I connect. That would be our complex number 3 plus 4i. If I just simply had 4i, there's no real part. So technically the real part would be 0. The imaginary 4. So if I come over here, I'm not going to go shift left or right any. I'm simply going to go up 4i. So that would represent 4i. Sorry, this one represented 3 plus 4i. Now if I go down, alright, we're going to continue to talk about complex numbers. Before we talk about complex numbers in polar form, let's represent our complex numbers geometrically. So, if we represent them geometrically, if I look over here, technically this looks like an xy axis. The x-axis, what we would call the x-axis, is our real axis. What we would call our y-axis is going to be our imaginary axis. So therefore, if I have a complex number 3 plus 4i, so my real part is 3. So if I write that as an ordered pair, my first number would be 3, then comma 4. So if I come over here and graph that, I'm going to go over to the right 3 and then up 4 units. If I connect that to the origin, that right there is representing 3 plus 4i. Now let's say I had -1 minus 2i. So the real part is -1. The imaginary part is -2. So I'd simply go over to the left 1, down 2, connect. So that right there would represent -1, 2i. Or sorry, -1 minus 2i. Now let's say I just simply had 4i. Well, there's no real part. So since there's no real part, my first value is going to be 0, comma 4. So I'm not going to shift left or right at all. I'm simply going to go up 4 units. So it's that point right there would represent 4i. Now, like I said, we can go ahead and write our complex numbers in polar form. So technically, our rectangular form of a complex number is going to be z equals a plus bi. In polar form, let's discuss how we would get the polar form. So we said a was the real part, which was my x-axis. B is my imaginary part, which was my y. Now remember, polar you're going to write in terms of r and theta. So remember, what does x equal? X equals r cosine. So if I come over here and replace x with r cosine, then remember y equals r sine. So I replace that I replace that y with an r sine times I. Now, if I take a look, what do both of these terms have? Well, both of these terms have an r, so therefore I can factor that r out. I'm going to move that I in front of the sign. And so I'm going to get r times cosine plus I sine. So this would represent the polar form of my complex number. Now, there is a shorthand for this, and the shorthand for this would be what we call r cis. So if we don't want to write the cosine theta plus I sine theta, you can simply write cis theta. And again, that is just the shorthand for that. So let's take a look at some examples. So number one, notice you're given your complex number in rectangular form and we want to write it in polar form. So therefore, if I want to get it in polar form, you're trying to convert it to r cis theta. So that's our goal right there. Now if I take a look at my complex number, my real part is 2. So if I write this as a coordinate, it's going to be 2, comma, my imaginary part is 3. So technically my x is 2, my y value is 3. Now again, let's think back. If I want polar form, I need my r and I need my theta. Well, remember, what does r equal? R equals the square root of x squared plus y squared. So if I go ahead and substitute those numbers in, I'm going to get 2 squared plus 3 squared. So 4 plus 9 is going to give me 13. So I'm going to get r to be the square root of 13. Now, the next thing we need to know is theta. So what is theta going to equal? Remember from sections 9.2 and 9.3, theta is going to equal the inverse tan of y over x. Now notice my x value is positive, so I don't have to add 180 in this case. So I'm going to simply say the inverse tan of 3 over 2. I would enter that in my calculator. My calculator's in degree mode, so I'm just going to round to the nearest tenth, and I'm going to get theta to be 56.3 degrees. So I have my r, I have my theta, so now I can write it as a in polar form. So my r is square root of 13. If you want to use the shorthand, you simply write cis, and then my theta is 56.3 degrees. So that would be my shorthand answer. If you wanted to write it out, my r is square root of 13, then I put comma, cosine my theta 56.3 plus I times the sine of 56.3 degrees. Both of these statements would be correct. They both represent the same thing. Let's take a look at one more example going from rectangular to polar. So again, the first thing I'm going to do is write it as a coordinate. So my coordinate is going to be -1, -2. So I'm going to go ahead and find my r. I square my x plus my y squared. So I'm going to get r to equal the square root of 5. Now I'm going to find my theta by taking the inverse tangent of y over x. But if I notice, my x value is negative. So remember, when my x value is negative, I'm going to have to add 180 to it. So if I use my calculator, I'm going to get second tangent of +2 is going to give me 63.4 degrees. But remember, I still have to add 180 to it. So I'm going to get theta to be 243.4 degrees. Now I'm just going to simply write this answer in the shorthand. So my r is square root of 5, cis 243.4 degrees. So that's how you would convert a rectangular to polar form. Now let's take a look at going the opposite direction. The opposite direction, you're going to have to use your unit circle and know your coordinates. So it gives you your complex number in your cis expanded form right here. So see how it's saying, what is the cosine of 11 pi over 6 and sine of 11 pi over 6? Again, you could go ahead and convert that to degrees if you wanted. So 11 pi over 6 in degrees is going to be 330. So I'm just going to make a mental note. What are my coordinates at 330? Well, my coordinates at 330 are going to be the square root of 3 over 2, comma, my y value would be -1/2. So now all I'm going to do is substitute these values in. So there's a 4. It says cosine of 11 pi over 6. Well, what is cosine? Cosine is simply my x value, which is the square root of 3 over 2, plus I. What is the sine of 11 pi over 6? The sine of 11 pi over 6 is -1/2. Now all we're going to do is take that 4 and distribute it in. So 4 divided by 2 is going to be 2, so I'm going to have 2 square root of 3. 4 divided by 2 is going to be 2, but I have that negative, so it's going to be -2i. So there's my rectangular form. Let's end with one more example. So again, I come over here. It's giving it to me in polar form, so I want to change it to rectangular. So 5 pi over 6. What is 5 pi over 6 going to be equivalent to? Well, 5 pi over 6 is going to be equivalent to 150 degrees. So if we remember 150 degrees, my x is going to be negative square root of 3 over 2. My y value is going to be +1/2. So I'm going to just simply take this statement right here and substitute the correct values in. So I have a 2. The cosine is my x, so negative square root of 3 over 2, plus I, my y value, which is 1/2. I go ahead and distribute in. My 2 is going to cancel, so I simply get negative square root of 3, plus my 2's cancel, I just get I. So I'm going to get negative square root of 3 plus I. So from here, I want you to go ahead and work on the complex numbers worksheet. If you have any questions, just write them down, and I will make sure to answer those questions. I hope everybody has a great spring break, and I'll see you when we get back.